So speaking of controllers, let's look back at kind of our block diagram and kind of revisit some of our block diagram algebra for for closed loop systems. So we can calculate the transfer function from our output over input, and this would be related to essentially our tracking, right? You could also put the error over the reference, and this would be essentially our tracking error. We can also look at the regulation effort, which is the error over, basically the ratio of the error over the disturbance, right, applied to that system. So regulating, trying to minimize essentially those disturbances. And your control effort, which is what's your command output as a function of the reference. So these are all very, very important transfer functions that can tell us and give us some insight on the system. It can relate back to our, some of our goals of control design, and also can be utilized to see is the controller performing well, depending on what we have. One of the cool things is across all of our closed loop transfer functions, especially for closed loop feedback systems, this is always going to be in our denominator, that 1 plus Cp. In the numerator, though, that can change, but depending on our ratio, so if we have y over r, we see in this table that Cp. So Cp over 1 plus Cp is exactly what we see right here. Haha. Bad joke. But you can leverage this table. I think it's a really, really useful table to kind of just, if you're trying to kind of figure out those values or look at different transfer functions, you can immediately, you don't have to go through the block algebra or the block diagram algebra each time. You can just jump right into it. So we need to make sure, essentially, this is only for closed loop transfer functions, depending on the controller. And remember, we have to still be stable. So we need to be stable. All of our poles must be less than 0, satisfy our stability criteria. We can investigate or actually quantify tracking with this transfer function. And you see, as you increase C, this ratio becomes lower. So the error as a function of the reference becomes lower. So it reduces the quantity, leads to better tracking. Regulation, you can see here, larger C will suppress essentially this value here, right? So as we increase C, that value of error over disturbances gets smaller. So we're suppressing essentially this disturbance. It has higher authority. So it dominates the behavior of that system. So from here, just the simple answer would be just increase C infinitely, right? If only engineering was that simple, and realistically, if only we had enough money to do those things. If you look at the controller effort, however, we increase C here, this effort's going to be really, really difficult. So again, burn out the motor, all that good stuff. It might not even be possible. So larger controller, better tracking, disturbance rejection, more control effort. Smaller, less effort, poor performance. And we'll kind of see that in our, in our inverted pendulum, there's a limit. I mean, as much as I wish I could buy, create a huge, runway and really, really fast motor and everything like that, there's a price limit to these things. So, and that's life. And you'll see that a lot in industry and academia and everywhere. Let's look at, a gain controller again. So if we have this plant function, we have this controller, we know we can kind of shift and keep it stable or unstable. And you can see essentially the response of that system as well. So we've already seen one example of this, but we can kind of quickly, especially since I have my manipulate plot here. So what we can do is we can actually see how the response changes. And here in this particular system, we have to be greater than 2 to stabilize. So if I'm here, you see here, so 1, I'm just exponential increase, but finally, once I hit that, if I type in 1.9, increasing, if I do 2.1, you can see I'm starting to level off. Once I get to 5, my system is basically stable there. So we're shifting essentially those things. You can see it essentially in the poles as well. And so that's kind of the key idea. And we've seen that before. But we can also look at the control effort. So the control effort is going to look like this. And we can look at and derive from the control effort our control command, U of S. So we can actually see what is that going to be. So what we can do is, so this is my control effort. If I just do it times, our R of S is just going to be this time unity. So I can get my U of T. And what we find is the following. And we can kind of interpret this. So as I increase, and remember I have to get past, so see, this is just going to negative infinity. But once we hit 2, right, we're stable. And you see that value, though, is kind of increasing there initially. So we're changing essentially this value here. So you can see the system for unstable, metastable, and the control response as we essentially change, you change that input there. So as you increase K, you improve tracking and speed up conversions, but you need increased actuation. You can exceed the motor limits, and you can kind of see the response. You can stabilize it here. Again, we need to make sure that we're in the right pole section here. And you can get a sharper response, but again, at what control effort, right? You see essentially those y-axis values we're changing as we're increasing essentially that controller, right? So here we're just completely unstable, so there's no meaning to that, control effort. And it asymptotes, but look at that y-axis value. Again, that control effort, that's difficult. So, excellent. We can even destabilize a system. So let's take a peek at this system. So it's first order, so we know S is equal to -1, so we're fine, right? We're stable. We have a controller. We can just play around with K and do whatever we want, right? Nope. So let's look at our system, because it's not anymore first order. It's actually going to be second order, as we're going to see. So I can take, for example, and you can actually see how that C effort changes as well. As you change here, we're positive, we're unstable. If we go past 2, we're at 2. If we do 4, now the pole or the 0 can be there. It's okay. Again, we can still have a stable system. So let's get this plant. Let's look at this control. We have a second order transfer function. So we should have 2 values here. And what we can do is we can say, all right, so we need to see, well, what value or where will this kind of put me in? So we can expand. We can basically, you can expand it. You can solve for it as well. So what we get, so right here, we're coming back. So we have this function now, and we can see, we can set some conditions on, our coefficients and what they have to be. So this is our discriminant. We get this value, which we already got. So now we can say, well, again, let's set it to 0. So let's say solve for when does this equal 0? That's K equals 1. Are we going to be at 1? So it needs to be less than 1. So you can actually see that. Let's just do that here. This may be silly, but again, I like to do this. Sometimes you need some convincing. Solve when does that equal 0? What doesn't like that? So for example, what we could do is we can say, because we've got 2 of our transfer functions right here. So I can say, let's pull this off. Flash dot K goes to, let's say goes to 3. Let's look at this. So see, this is positive now. So we're a little bit in trouble. We could even pull out this. It's just going to be the same thing, but negative, I imagine. I don't know why I didn't like that. Actually, it doesn't matter here. Negative, positive. I'm in big trouble here, right? So I'm already positive. I'm unstable. So if I'm 2, I'm still unstable. If I'm 1, I'm right at 0. So I need to be less than 1. So I need to be 0.5. 0.5, and then if I'm 0.5 here, now I'm stable, right? So ostensibly, I can just go and I can, if I set k to 3, we can see that here. If I set k to 1, now I'm okay. If I do it to 0.5, now I'm fine. So I could increase it 0.1, and you can kind of see that there. So as long as I'm less than 1, I'm fine, and I can stabilize the system. So you have to, but again, there's going to be some interplay as well. So we need to make sure, again, that location of the 0, it can stabilize it. So if it disrupts essentially those closed loop poles. So we need to make sure our k just can't be any value. So once we have that controller, we can actually, by adding the controller, we have destabilized an initially stable plant function. So that's the key idea. So we added a controller, we destabilized the plant, but we can also then tune the controller to restabilize the plant. That's a tongue twister, if ever there was one. So, but that's really the key idea. So even though the plant was stable, once we added that controller, and the controller is stable too, right? S is equal to -2. That's another, stable pole, right? You would think, okay, that's it. But again, it actually can destabilize that system. So make sure, essentially, again, we need to control these parameters: performance, control effort, robustness, tracking. We need to have stability. We need to have those performance and feasibility. Feasibility is a very underrated and incredibly important control design parameter. So make sure your design is feasible. We live in the real world. Make it such that it can, be successful in the real world. So we'll see you next time. Thanks. Bye.